Hello and welcome to the second lecture of software architecture. In this lecture, what we will do is we will have a brief history of software architecture. Let's understand what is the software architecture and how it came from, and then what people understand by software architecture today. So informally, I think all of us know what is software architecture. So, but let's look at it. Let's look at it more carefully, and then basically see what exactly the purpose of this architecture. Essentially, software architecture is a blueprint of a software. Now, blueprint for whom? Blueprint for the set of stakeholders to understand how the system would be once it is implemented. Very important. It's basically a blueprint for the stakeholders who and these stakeholders are all different or of different types. We will see who those stakeholders are and what do they understand or what do they want to understand about the system. So we'll understand that, and that makes software architecture really complicated. But at a high level, it is nothing but a blueprint. It is very similar to any design or any blueprint of any real life entities that we have all come across. For example, if you want to really design a bridge or a building or a car or a more complicated vehicle, people don't really start building or implementing those elements as soon as you understand the requirement. You first create a blueprint of those entities, for the bridge, for the house, for the building, for a vehicle. Create a blueprint and analyze a blueprint and basically show this blueprint to various stakeholders, and they all agree to it, and only then that an implementation of the blueprint is done. In software, the idea is very similar in the context of software. This particular blueprint is the software architecture. So question is what should be there in this blueprint then? In the blueprint, essentially you need to have a description at a higher level of abstraction than the objects and lines of code. So if you are building systems in object-oriented languages, first of all you have to understand what is OO language, what is a O paradigm, and then you understand, then you will appreciate that what is meant by a description at a higher level of abstraction. So it is certainly not at a level of code, it is at a higher level so that it is simple to understand, and the stakeholders can reason about the system, very importantly, without getting lost into a sea of details, because if they are lost into a sea of details, then the whole purpose is actually defeated. So the point is that it has to be simple at a higher level of abstraction, but should have enough content so that stakeholders can understand and reason about. So who are the stakeholders? If you are building a complex software, the software actually has multiple stakeholders who can expect certain features of the software. So these stakeholders expect certain characteristics, certain features, certain behavior of the software when it is implemented. Now you might ask a question that what happens in a scenario when the software is already built? Does it mean that the architecture plays no role? Of course, architecture plays a role there also. So in that case, and in most often what we have seen in software development is the software that is in existence for a long time Unfortunately, its architecture or the blueprint is not well documented. So to understand the software that is running and to improve, to modify, to re-engineer, to port, whatever it is, you first have to understand its blueprint. Therefore, you need to reconstruct the architecture. And during the reconstruction, you need to again look at the stakeholders, and then the reconstructed architecture needs to be validated through these stakeholders. For a new software, obviously the software doesn't exist yet, and these stakeholders will come and then they reason about the blueprint that's created, and then the implementation will start. Design and implementation will start. So in either case, in fact the second case is more prominent today, that as we find that there are hardly any scenario where people are building applications from scratch. There are already applications available and they are enhanced. So in that context, architecture reconstruction is important, but nonetheless the problem remains the same. You need to create a blueprint, and then you need to understand, identify the stakeholders, and then get your blueprint validated through these stakeholders. So who are these stakeholders? These are the examples, but that doesn't mean that you have to follow it really blindly. This is just a guideline. The stakeholders identification is an important task of an architect. So you as an architect, when you are dealing with the software, you have to spend time to find out who are the people who are really concerned about this application, and they would be your stakeholders. In this example, the stakeholders could be the chief technologist of the company or of the particular line of business or the particular product line, whatever. So the area of concern, again, I have created at a very high level. So for the chief technologist, the area of concern is that does it really adhere to the organization standards? If you are dealing with really a large corporation, let me give an example. Suppose you are dealing with a large corporation like a bank, a multinational bank. So the multinational bank today, the amount of software that they build or use is enormous, and this bank might have different lines of businesses, and there might be chief technologist per line of business, or there could be single CTO or chief technologist for the entire organization who is interested about the software that you are building or you are analyzing. So the first thing is that, and for the chief technologist, really the questions are, does it really adhere to the organization standards, as in the organization, the corporation as a whole would be defining certain technical standards, certain policies in place, and every single software that's built must adhere to those policies. Examples are, the policies could be that one could say that I'm not going to use open source at all, or it could be I'm going to use only open source. The policies could be that I'm going to use let us say the inbuilt or in-house components as much as possible. Policies could be that I am going to use only C++ based implementation. Policies could be that I am going to use only message bus related architecture, meaning that my entire organization, all the software must communicate with each other through an internal message bus. So this example is really a strong, it has a strong architectural implication. So these are the things that chief technologists would be interested, and your architecture must conform to or address this concern. So these concerns are kind of questions, expectations. You can treat that as a expectation also. Then the database engineer essentially would be interested about things like what information should be stored, where it should be stored. If are you going to store that in a co-located database? Are you going to distribute it into multiple different geographical locations? How these are going to be accessed? How they are going to be replicated? How they are going to be preserved? What are the information security issues? These are the questions, doubts, or concerns that the database engineer would have. As an architect, you need to address those. Again, I highlight and I repeat that these questions are just examples to give you an idea. You have to come up with the specific area of concern when you actually go and then do the architecture assignments. Application development team would be having a very different set of questions. For example, questions like, how do I implement a complex scenario? How should I organize my code? How do I plan for division of work? Who should do what? These are the questions that the development team should have from the architect, that architect needs to address. Users or customers will have questions like, does it perform as per my requirement? So has it implemented all the requirements? What about the cost and budget? Has it overrun? Is it under? Is this cost and budget controlled? What about performance and scalability? How well those things are addressed? How easy it is to use? Is it always available? Then the infrastructures team who is going to deploy your software. If it is a software that's, for example, in a bank, let us say you are going to deploy the software and that's going to be used by many people. So obviously the infrastructure manager would be interested to know certain things. Again, they will be asking about performance and scalability. They will be asking about the amount of network usage that it's going to have. What is the plan that you have thought about in terms of the network usage? Examples are, let us say that you are going to have the system installed in a particular location, and for a moment assume that this particular application is going to be used by many people across different geographical locations, and you have a particular requirement that essentially this particular application must be able to respond within certain time. Point is that if those people are from different geographical locations, and then how do you guarantee that people who are in Europe versus people who are in South America will be able to really get the same level of response? Are you going to really do that? Or you have to say upfront that no, I'm not going to address this. So these are the things that need to be addressed at the beginning. You cannot be completely ignorant to all these aspects. It is okay to say that I will not be able to provide such feature, or I will be able to provide the feature. It's okay to say no, or it's okay to say yes, but you have to be explicit. So that's how you need to address the area of concern. Area of concern does not mean that you have to say yes to all of them, but you need to give an answer which all of these stakeholders must agree. So indication of the hardware and software cost, scalability issues, deployment location, safety and physical security considerations. These are the things that infrastructure manager would have. You need to address those. Is it fault tolerant? Does it have a crash recovery mechanism? What are the backup techniques that or scenarios that you have thought of? So these are the things that infrastructure manager might ask you. They may not ask all of them, but these are the possible questions or concerns that they have, and if they have, as an architect, you need to have an answer. So therefore, in the blueprint, these things must be addressed. A release and configuration manager would be concerned about the build strategies, how application is going to be built. Is it nightly build? Is it fortnightly build? Is it weekly build, etc. So build structure, build strategy need to be addressed. You need to be there to ensure that such build strategies are in place. Code management, version control, code organization is not your concern, meaning that you really will not be involved in doing this, but you must be there to ensure that such things are done according to your guidance. Therefore, as a part of the architecture document, these things must be explicitly mentioned. How do I then the system maintenance team will have questions like, how do I replace a subsystem with minimal impact? So if that's a requirement, then you need to really address that as a part of the architecture. How quickly one can diagnose a fault? How do you have a much better fault and failure recovery mechanism? So these things must be addressed beforehand as a part of the blueprint. So let's look at some very fundamental question, that why do we really need the architecture to be described? So on the left hand side, if you see, I have put a box, and then I have basically provided a list of some important characteristics of a large corporation. So typically in a large corporation, there are hundreds of concurrent projects that are being executed by different teams. Team sizes vary, could be 10, could be even 100. Now these projects capture requirements. There are architects and there are large development teams. So architects start with the requirement team and then hand it over to the development team. That's generally the practice. Now in a large software corporation, typically these things are a very common practice. The question is that in such a scenario, why architecture is important, why architect's role is important, is that on the right hand side, if you see those 5 bullet points, let's understand those points in detail. So in such a scenario, each stakeholder for a given project, often you would see that the projects or the project teams, they hardly interact with each other. They're all living in their own silos. So each stakeholder, they have his or her own interpretation of the system. So if there are 2 project teams, a stakeholder from one team will have one interpretation of the system, and the stakeholder from another project team might have a very different interpretation of the system. Sometimes they don't have any understanding at all. In that case, as an architect, you would play a role of a middleman who is going to coordinate with these stakeholders and bring them to the common ground. Then the next role is that how will everyone be convinced that his expectations from the system will be satisfied? As I said, that architect is a middleman. An architect needs to convince everybody. So essentially, through the architecture, you should be able to convince all the stakeholders that I have identified in the previous slide. You should be able to identify them and then reason about the architecture in such a manner that they are convinced that their expectations, their requirements, their concerns are all addressed when the system is built. Now, even when the architect has created the solution blueprint, question is that how does architect hand over the solution to the developers? That's possible only when there is an architecture. Without that, it is not possible to really hand over the solution blueprint that architect has created by talking to these stakeholders and give it to the developers. In order to really hand over the solution to the developer, you need something concrete, and concrete to an extent that the development team understands what your solution is. So you might be able to explain, you might have explained the stakeholders, and typically they are senior people, so they might have understood, they might have convinced, but you need to now hand over the solution blueprint to the more junior set of people who are developers. For them, it should be sufficiently detailed so that, and they are going to ask many technical questions which most often those stakeholders will not ask, at least people who are at a senior level. So to really address their technical questions, you need to have the architecture sufficiently detailed so that they understand what is your solution, and then implement the system accordingly. Next question is that how do the developers build and ensure different critical aspects of the system? Now that's again implemented, or that's again realized by architecture descriptions. Essentially, as an architect, you need to address some of the critical aspects of the system, how they should interact, how they should implement, how in fact how this development team should implement, so that those critical aspects are actually designed, developed as per the requirement. Remember that for simple scenarios you really don't require such detailed description, only for the critical aspects, like let's say sub-second performance, how such performance scenarios would be addressed. What about really high load conditions, how the system should behave? What about security attacks? What about things like failure, how fast it can recover? So these are the critical scenarios, and most often these critical scenarios are not really functional, they are oftentimes non-functional. So as an architect, you need to really help the developers in describing those critical aspects and how they should be implemented. This is a part of architect's responsibility, and the architecture document should have this information. Now, misunderstanding actually leads to incorrect implementation if these are not documented properly, and that's what is this, unfortunately, the scenario even today. If these are misunderstood, it leads to incorrect implementation, and incorrect implementation means that it leads to 10 times more effort to fix at a later stage, 10 to 100. In fact, if there is a mistake at a architecture stage, if it can be fixed quickly, but if that mistake is not really caught or understood or misunderstood, and then what happens is that after implementation, when you are doing testing, that time the cost of fixing that problem will be at least 10 to 100 times. So therefore, it is highly important that the blueprint is done really well, architecture is done really well, so that such misunderstandings are not there, such errors are not there, so that you don't have a costly fix at the time of testing or even after deployment. So let's look at the software architecture definition. Unfortunately, people really do not have one single definition. There are many definitions and they are similar in nature, but there is not a single one that exists today that that everyone knows. But if you look at their definitions, as I said, they look similar. So let's look at some of the definitions that are there in different books, different papers. One of the important definition is that it says architecture is nothing but a structure or structures of the system which comprise software elements, the externally visible properties of those elements, and the relationship among them. I have highlighted some of the keywords in bold because those are important. Software elements, externally visible properties of those elements, and relationships. Let's look at the second definition. It says description of elements from which systems are built, interactions among those elements, patterns that guide their composition, and constraints on these patterns. In general, a particular system is defined in terms of collection of components and their interactions among these components. So again, look at the keywords like components. This is similar to software elements. Then it talked about interactions, which is basically relationships among them. Then it talked about patterns, compositions, which are again relationships. Then the third definition is, and these are all important definitions, description of the subsystems and components of a software system and a relationship between them, subsystems and components that are typically specified in different views to show the relevant functional and non-functional properties. So a new keyword called views, and otherwise it is the same set of keywords like subsystems, components, which are more or less used by the other people. Now these people like Bass, Clements, Kazman, Shaw and Garland, Felix Bushman, these are all real pioneers of software architecture. They have contributed to the basic the discipline of software architecture. So, and whatever we do today in terms of software architecture are basically due to their contributions. Therefore, it is very important that we understand what they are saying, how they are describing when they talk about software architecture. So, in the previous slide, I have basically highlighted some keywords like software elements, components, their relationships. So, more or less, what comes out to be an architecture is that it is basically software elements, their properties which are externally visible. Very important. Externally visible means that whatever that can be seen from outside. It is not really important to describe how the system, how the subsystem, or how the component is going to implement certain properties. So how part is not important, but what it implements is important. Example is that suppose you are building an application in which there is a module which deals with, let's say, users of the system. So externally visible properties could be that how a new system is built, how the new user is actually created in the system, how a existing user is modified, or its characteristics are evaluated, modified. So these are the externally visible properties. In other words, an externally visible property of a subsystem is the set of functionalities or features that it exposes through its interface. So what those definitions are talking about is about defining a set of subsystems, and each subsystem should have very clearly defined functionalities or features that are externally visible. Very important. And you are not going to describe that is internal so far as the architecture is concerned. Internal parts will be relevant for designers and developers, but not for the architecture. So if you look at this particular diagram here, it has got 5 boxes: viewer, composer, protocol engine, storage, utility functions. They're interconnected. One is top of another. Question is that, is this architecture? And typically we describe architecture as a collection of diagrams like this. Most often you see that in any architecture, a description in industry is a diagram which looks similar to this. Plus there are many other diagrams, but you will definitely have diagram like this. Question is this architecture? So the answer is no, because it is ambiguous. Why it is ambiguous? It is ambiguous because it's there is no visible responsibilities. What do they do? What are those modules? How does their function relate to the system? How have these elements been derived? Is there any overlap? Meaning that is it? Are you sure that one module is not implementing, or rather two module? Are you sure that the two modules are not implementing same thing twice? Um, that's not one does not know by looking at the diagram. Are these processes or they are programs? How do they interact? What do those lines mean? Are they really distributed? How they're deployed on a hardware? What information does the system process? What is the meaning of this? One box is on top of another. What does that mean? So these questions are really not answered. So these are all ambiguous things, which is why this is not an architecture. Unfortunately, most of the architects, most of the people call the diagram to be an architecture. So yes, what I was saying is significance of the connections. How do they interact? How do they communicate? Those lines means nothing. The lines just mean that they are connected, but what does it imply? It's not clear. Significance of the layout, one is top of another. What does it really signify anything, or it's just or it's just done due to space constraint? It's not very clear, which is why this particular diagram serves no purpose at all, other than the fact that there are few boxes and their names and they're connected. So from architecture point of view, this diagram serves no really purpose. So then the next question is that what should the architecture description have then? Well, the architecture description should at least have a structure having a set of modules. Each box you can call them as modules, but it should clearly have a set of services offered by each module. It should be clearly defined. Their interactions should be defined to achieve the functionality. In the example that I gave, the user management module, which is dealing with creating new user, adding or modifying an existing user, if that's a module, then you need to define that how this functionality is achieved. By how I don't mean that it's internal implementation, but what I mean is that does it take help of other modules, other components to really fulfill these features? So that must be described. Information and data modeling is a part of architecture. Achieving quality attributes should be there as a part of architecture. We will learn this later. Processes and tasks that execute the software, that must be described. How the software is deployed into hardware, that must be described. And the development plan, that must be described. So essentially there are 6 elements that you need to address here: the modules, the information, achieving quality attributes, process views, how it is deployed, and how it is developed. These are the things that one must describe as a part of software architecture. Continuing with it, in addition to the structure, it should have a behavior also. And what is a behavior? It basically describes how the structural elements execute important and critical scenarios. Remember that I was talking about a case where the development team might ask you that how do I implement a complex scenario? And those complex scenarios are typically non-functional scenarios. Now, as a part of the behavioral description of architecture, it is important to basically show how a system authenticates. For example, how a system is going to authenticate a mobile user. It might be a critical scenario for a given application. So as an architect, you need to illustrate how authentication process is going to happen so that the developer or the development team can implement it. Next question is, how does a system process 1 terabytes of data in one day? Now, it's a question of huge high volume data processing. You need to illustrate how this data acquiring process will happen. How does the system stream video uninterruptedly during the peak load? This is also a scenario that you need to describe if you are implementing such a system. Now these scenarios are essentially implement various quality attributes that we will learn later. Let's look at a part of the architecture. This is Windows architecture. I have taken this picture from MSDN blog, reasonably recent. Now what you see here is that well, as per that definition, this particular diagram is certainly not an architecture, it is a part of it. But at least it gives I mean, I have not really taken the entire architecture document, but just taken one picture of it, which is basically the picture of the different modules. So if you look at it, there are modules like kernel runtime or hardware abstraction layer, which is at the bottom. Then on top of that there is the object manager. Then there are other components. There are device drivers, device handlers like net devices, net protocol handlers, file filtering systems, volume managers, device tags, and so on. Then there are GUI components. There are kernel 32, there are different system services, and so on. Now they have used different color codes to indicate different types of modules. I mean, you can also use that as long as you explain what those color coding means. Let's look at another example, an Android operating system, an Android architecture actually. So as you know, the Android platforms are very popular today for mobile application development. So it's interesting to see at least a part of the architecture here. Here if you see that at the lowest level there is the kernel module, which is basically the Linux kernel, which has got different modules. So things like display drivers, camera drivers, Wi-Fi drivers, etc. These are there at the lowest level. On top of that there are different libraries, and there is an Android runtime component. There is a virtual machine. There are OpenGLs for the graphics processing. On top of that there are application frameworks that are typically used, that are given actually to the developers to build their own applications. I'm not going into details of those, but at the topmost level you see that there are actual applications like phone application, browser application. You can add new applications there, which in turn can use these application frameworks. One important thing to note is that these modules are actually described using a stacked manner. Like there's a kernel at the bottom, then there are libraries, then there are framework applications. This stacked mechanism of description is also called layered pattern. We'll learn that later on, but this is a very common way of describing, and there is a very specific meaning of having this kind of stacked architecture or the layered architecture. It has its own semantics. We will learn that later. So that's all for this particular lecture. In the next lecture we will learn more about different architectural styles and views. Thank you.